So we begin chapter 15 with 15.1 with graphs and level curves. So this is the first time, well, maybe not, the first time you get to look at functions of multiple variables. So, and believe it or not, you have worked with them, but not the way we're working it in depth this time for the first time. Because what we're going to do, understand and use the notation for a multiple variable function. We're going to determine the domain and the range, possibly not the range. It might be difficult to look at the range of a function describing a surface, but for the most part, we're going to go and find the domain for multiple variable function and use that information to describe the graph of a two variable function. What else? We will sketch level curves for two variable functions, and we will sketch the level curves and describe the level surfaces for three variable functions. Of course, we're not going to look at four variables. That's something hard to or impossible to visualize, at least as of now. All right? Okay, so multivariable functions. So, what about it? Well, it's nothing new in a way as far as the notation. It's how we're going to put more variables essentially. So we have worked so far with functions with one single independent variable, and then for that particular input we're going to get an output which is a number that of course it's defined if for that value of the input the function it's defined at that value. I mean, if it's not in the domain, then we just don't, right? So, let's go back to basic algebra. F of x equals to y. So, oftentimes you would use this notation interchangeably. Here you would use f of x, you would just use y, depending on the purpose. But actually, this helps us see what's going to be the independent variable. And recall that the independent variable here, it's always the letters you would see in parentheses when you use the F notation. That is, input, which is the independent variable, and the output, which is the dependent variable. And I mean, I'm pretty sure you've seen this machine approach, right? No. The classical machine approach where you have some input. The machine is going to do some function, and it's going to output a number or something like in real life situation. We can compare the domain of a function as the OK inputs for a function. For instance, for f of x equals to 1 over x plus 1, is that function defined for all real values of x? No? Is that function restricted? For which values of x is that function restricted? -1, all right? So that means if this function right here is described by this machine, if you input a -1, what's going to happen? It's going to blow up, right? Think of a coffee machine, for instance, right? So what are the OK inputs for a coffee machine? Okay, ground coffee. What else? Water. What else? Just that? Well, have you tried making coffee with some pieces of cinnamon with spreading in the filter with the ground coffee? That's a good way. It's a really nice coffee. How about shredded Mexican chocolate? That's basically a mocha, homemade mocha. So try that next time. So that's another OK input. Maybe some almonds to get the essential oils out of the seeds, or hazelnut. That's how you can actually create your own syrups, the hazelnut, rather than buying the bottle. You get them naturally, and using the hot water. That's how you get. So it's not very limited what you can do with a coffee machine. But what if I put gasoline into the filter? What's going to happen? It's going to blow up, right? That's basically the x equals to -1 for this function, right? The gasoline into the coffee machine. Maybe if you're lucky, well, of course, I'm pretty sure it's gonna blow up. So that's what we're gonna do in this chapter. Well, in this section, find domains and ranges of functions of multiple variables. So all those rules that we reviewed to find the domain of a function for a vector valued function, those are gonna come back for functions, but not just for the variable t, but for two variables x and y simultaneously, x, y, and z, or there is no limit as to how many variables can you add into your function. And well, we should be able to describe their restrictions based on whether we have some radicals, maybe some arc sines, arc cosines, what else? Logarithmic functions, and we're going to look at a few cases of it. So maybe not all of them, maybe not too many, but first of all, let's describe the notation for a multivariable function. Okay, so again, back to algebra. F of x equals y. X is the input variable. That's the independent variable, what you can control. You know, again, coming back to the coffee machine example, you can choose how many grams of ground coffee, how much cinnamon, how much chocolate you want to add, how much water. So you can control that. If you want to obtain a really dark coffee, you would put less water, more coffee, or vice versa. If you want a lighter coffee. And well, that's actually the output. The y will depend on how you control the input variable. So the output cannot be controlled. The input can be. All right, but I mean, what's the notation for functions of multiple variables? Well, so if we have a function of two variables, we would just change what happened here. We would change our f notation. Okay, in a second. Okay, there you go. Let me change to blue. Okay, so instead of having f of x, we're going to have f of x y, all right, equals, typically we call z to two variable functions where the inputs are going to be, what's that? Two variables. The input is two variables, the output is one variable, like the very simplest coffee, right? Just water and ground coffee. What's the output? Z, water with coffee, right? So the combination of the two. Of course, you can add more stuff to it. So add a third variable, f of x, y, z, equals to, typically for a three variable function, we call this a W function. Of course, again, as I mentioned before, there is no, oh, by the way, there's a little typo here. This is not supposed to be a 2, but actually 3. You can define another function, f of x, y, z, w, u, v, theta, omega, rho, phi, as many variables as you want, right? And call this simply, maybe, I don't know, maybe big F if you want. Typically we call it big F or big G. That's going to be later when we get to find gradients and directional derivatives. Well, all right. How do we work with these functions? Well, the same way. Input, output, substitute, plug in. Let's have a look at a couple of examples. Evaluate each multivariable function for the given input value. So we're given the function z defined as f of x, y. That is, the inputs are x and y. That is, it's a two-variable function, and the output will be one single variable. All right? So that means all we're going to do is substitute -1 wherever you see the letter x, and 2 wherever you see the letter y. As easy as plug and check, right? That is, okay, so -1 squared times 2 minus 5y, which is 2, plus x, which is -1. And simplifying all this, that's going to give us a -1. All right, so just to give this sense of formalisms, what are we essentially doing in terms of transformations, if you will, especially for those of you who are math majors or some engineering majors who may need to see this. Essentially, we're going from a function in R2. So our input is an order pair, and our output, it's just a single value. All right? Let's have a look at the next example. So for the next example, W is a function defined for three variables, x and y and z. Okay, e to the x minus z over y. They're asking us to evaluate f of 0, -1, 2. Okay, I mean, if it works for you, substitute 0 wherever you see the letter x, substitute -1 wherever you see the letter y, and substitute the 2 wherever you see the letter z, the variable z rather. And again, e to the 0 minus 2 times z, which is 2, divided by y, which is -1. E to the 0, that equals to 1. 2 times 2 in the numerator, that's 4. Divided by 1, it's still 4. Also, negative over negative, that equals to positive. So 1 plus 4 equals to 5. And again, to be more formal with the computation we're doing, so this is about going from R3, that is our input, it's an order triple, and our output is just one real number. All right? I mean, technically, if we get too technical about it, technically these are also complex numbers, but in this case, complex numbers whose imaginary counterparts are 0. But well, imaginary numbers, complex numbers with multivariable functions, those may come later, not today. Okay, in the same way that we can determine whether a given relation is a function or not a function, we can do this in space. So in the same way that we did, for instance, we have a couple of graphs like this, you know, and maybe this graph versus a hyperbola, for instance, right? Is the first graph that of a function or not a function? Function? How come? Passes the vertical line test, right? Vertical line test, everywhere you trace it, it's just going to cross once. I suppose, or unlike the hyperbola, which crosses more than once, so that's not a function. I mean, think about what a function is and what not a function is here. So essentially, for the different value of x, we're getting two different values of y at the same time. It's like being in two different places at the same time, right? Is it possible to be in class Calc 3 at 8 a.m. at the same time as at the beach? It's not possible, right? So that doesn't define a function. So that's how you can relate this function idea with just or versus a relation only. Well, of course, we can take this to the 3D space. For instance, think about that ellipsoid. And it doesn't matter how you trace this vertical line. See how this vertical line, it's crossing 2 points on the ellipsoid. So for this reason, that surface right here does not describe a function. So not a function. All right. What about the paraboloid to the right? Well, actually, that one describes a function because look at that. Look at the vertical line test. Notice how it's crossing only 1 point, right? So that means it is a function. Now, I mean, here is the thing with vertical line test in space because, I mean, in the plane, x horizontal, y is vertical, easy. However, in space, depending on our point of view, our vertical could be in the direction of z, our vertical could be in the direction of x, or our vertical could be in the direction of y. I mean, in space, it's weird. So, in this case, this is the equation. This is a paraboloid, which is described by z equals to x squared plus y squared. I'm just going to go with the simplest case. Of course, there might be coefficients such as 2x squared plus 7y squared, that's going to give us an elliptical paraboloid. But well, let's consider the easiest case. But the reason why I am talking about these different ways to see vertical, if you will, that is, what if our vertical is parallel to the x-axis? Well, in that case, how many points is that vertical line crossing on the paraboloid? What about parallel to the y-axis? How many points again? So in those cases, it's not a function, right? It's just a relation. Well, how is that? How can we relate to its algebraic form? Well, in this case, here, z equals to x squared plus y squared. Our inputs are x's and y's, order pairs in the xy plane, and our outputs are points whose height are at whatever z value, all right? However, in this case, when we have the variable solved, that is, we have an explicit, we have solved explicitly for z, then we may be able to define z as a function of x and y, equal to x squared plus y squared. Okay, we already mentioned that if we use this, if we do this vertical line, vertical line in the parallel to the x-axis or parallel to the y-axis, see what's going to happen. So, in this case, that means, let me do one case. That means that if I want to solve for, say, let me solve for x. X squared equals to y squared minus z. And then I would like to solve for x. But did you see a problem with x? With solving for x? That's square root of y squared minus z. Actually, plus or minus, it's outputting two results, two functions for this function. Something a plus and a minus. That means for every y squared minus z, we are obtaining two results. That is, again, we are in two different places at the same time, right? So if we were to define x as a function of y and z, then in this case we would have two cases, minus the radical and plus the radical. That's essentially two results. That's the algebraic representation of this vertical-ish line, or rather crossing 2 points on the surface. All right? So, okay. So let's have a look at finding domains of multivariable functions. All right. So let's go to the next page. Find the domain and range. Well, let's just find the domain, so not the range. Again, in some cases it might be possible, not in every case. So find the domain for the function f of x y equals to 4x squared plus y squared minus 16, and give a complete description of the domain in words and including a sketch in the xy plane. So guys, this is going to be our one of the most important tools in functions of multiple variables. That's because based on what we understand in this chapter, we need this when we get to the next chapter, when we get these regions in the xy plane to define double and triple integrals. So knowing the domain facts, also knowing how to sketch this in the xy plane, it's crucial for what's next. Of course, when we get there to the double and triple integrals, I will be bringing a lot of GeoGebra solid so you can visualize over what we're integrating in the life. Okay, all right, so let's get to this one. Interesting. Square root of 4x squared plus y squared minus 16. Okay, so any ideas? Okay, number one. What if you had something like y equals to the square root of x minus 4? How would you find the domain of this function? So set x minus 4 greater than or equal to 0, x greater than or equal to 4. Alright, that means the domain of this function is all values that are greater than or equal to 4. If you substitute at 3, that's 3 minus 4, that's negative 1. That's a complex number or imaginary number, if you want to call it. So This one has a restricted domain. How is that going to look? How is this going to look like anyway? Well, so we're going to do the same. So we're going to set the radicand, both variables at the same time, for x squared plus y squared minus 16 greater than or equal to 0. All right? Are we going to solve for one variable at a time? No, we're not. So you will see how is that going to work this time. So because in this case we have what we think of a quadratic inequality in two variables, somehow there's going to be a conic section. Just to give you the heads up of where we're going. For x squared plus y squared equal or greater than or equal to 16. Well, this is not the typical representation of a conic. So conics, when we have both variables squared, maybe one positive, maybe one negative. So we want to have a 1 on the right hand side of the equation. So I'm going to divide both sides by 16. So x squared, 4 over 16, x squared over 4, plus y squared over 16, greater than or equal to 1. All right. What does that remind us of? X squared over 4 plus y squared over 16. And let's pretend the greater than or equal is an equal only, equal to 1. What is that? It's an ellipse, right? It's an ellipse where a equals to 2 and b equals to 4. Well, plus minus, right? Technical plus minus. That means this a and b are going to give us the intercepts. Well, in this case, the intercepts in a more straightforward fashion. That's because this ellipse is centered at the origin. But of course, we may get cases in which this ellipse or any of these conic sections are shifted. You know. So, but in this case, for this simplest case, we're going to have this what's it called? This centered at the origin. Okay, let's graph this. So I'm gonna do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2. Let me see if I can get this right. Oh, okay. So okay. Let me do the ellipse like this. All right. There you go. So that is our ellipse. So that is centered at the origin with x-intercepts at plus and minus 2 and y-intercepts at plus and minus 4. All right. But hold on, we're not just graphing the equation, we're not just graphing the ellipse. We're graphing a non-linear inequality. So that means, coming back to what we learned in either pre-calculus and also in an intermediate algebra course, so you might recall that when you're graphing non-linear inequalities, this ellipse will divide the Cartesian plane into two regions to shade, right? So we're going to shade either inside of the ellipse or outside of the ellipse. Well, there's a couple of ways to go about this. Number one, and the one that you might remember is by just substituting any random points. You know, like 0, 0, which is usually the typical or the easiest. Like 0 squared over 4, that's 0, plus 0 squared over 16, that's also 0. 0 plus 0, is that greater than or equal to 1? False statement. That means we don't shade where the point is, but we shade on the other side of the bound, that is outside. That's the analytic way, the more formal way. All right? However, the easy way, so to speak, is to just look at the inequality symbol. Greater than means outside, while less than or equal means inside. So in this case, because it's greater than, I'm going to shade outside. All right? Whoops. So we shade outside of the ellipse, not inside. Okay. So that is the graphic representation. And well, let's just specify. Means careful. This means, okay, in words, all points outside and on the ellipse. Right? Also on the ellipse. Is there a case where it's only the points outside but not on the ellipse? Well, what if instead of the radical function you have f of x, y equals ln of 4x squared plus y squared minus 16. So to find the domain of a logarithmic function would be similar. Set the argument in this case only greater than 0, not greater than or equal. How would that change for the graph? Well, this ellipse wouldn't be a solid ellipse. It would be a dashed ellipse in this case, all right? And this inequality symbol only be just greater than, not greater than or equal. All right, now here is where we need to pay special attention about how we find the domain of a function. Well, so coming back to f of x equals to x square root of x plus x minus 4, we express the domain in set builder notation x such that x greater than or equal to 4, or using interval notation, that is 4 to infinity. Close for 4, open for infinity. Now here is the thing. There's no interval notation for functions of two variables because we can't do that. I haven't seen it before. I don't think there's a way. So we will do only the set builder notation. How do we express set builder notation for functions of two variables? Well, the domain, that is, instead of just saying x such that blah blah blah, in this case it's all the ordered pairs x y such that x squared over 4 plus y squared over 16 are greater than or equal to 1. So let's compare these two. Here, the domain of this radical function is all the real values x such that they are greater than or equal to 4. And in this case, since we're considering two variables at the same time, it's all the order pairs that are essentially on outside and on the ellipse. And that's how we express this. Now, what if? I like doing these what ifs. What if f of x, y equals the cube root of, not the square root, the same function, but under a cube root? What would be the domain of this function? All real numbers. Let's be specific. Oops. Let's be more specific. So the all real numbers part is correct. So in this case, we would need to say that it's all real numbers for every single variable. That is, all the order pairs x, y such that, number 1, x belongs to the set of all real numbers and y belongs to the set of all real numbers. All right? So in this case, this function is not restricted. It's all real numbers for both. We need to separate by commas. This x belongs to all real numbers, y belongs to all real numbers also. All right? And